I wanted to solve a problem that involves work done and involves changing kinetic energy. Two of the topics that we discussed in Lecture 9, two of the topics we introduced in Lecture 9. So in this problem, we've got a crate on a horizontal floor. We're told that the crate has mass 8 kilograms. We're told that the crate is pulled across the floor with a 20 Newton force that's acting 30 degrees above the horizontal. We're told that there's friction between the floor and the crate, and the coefficient of friction is 0.12. And finally, we're told that the crate is moved 1.2 meters across the floor. So with all that information about the crate, about the floor, about the movement of the crate across the floor, we're asked to figure out the net work that's done on the crate by all the forces that happen to be acting on the crate, and also figure out the changing kinetic energy of the crate as it's moved across the floor. Okay, so I'm going to start with a sketch of the crate and the floor. Add to it the things that I know in the problem, like the mass of the crate, the coefficient of friction, the distance moved. And then add to that diagram all the forces that are acting. And by thinking about those forces that are acting, it'll lead me on to calculating the work that's done by those forces that are acting. So here's the crate and the floor. And we know that the crate moves 1.2 meters. So that's the magnitude of the displacement, and it's to the right. And we know that there's a coefficient of friction. It's kinetic friction, and it's 0.12. And we know the mass of the crate, 8 kilograms. So those are the things we're told in the problem. Now let me add the forces that are acting. So one force that's acting, of course, is gravity. That's vertically downwards. That's the weight. Another force that's acting is the pull that somebody's exerting on the crate. That's going to be called F, and it's 20 newtons in strength, and it's directed 30 degrees above the horizontal. A third force that's acting is a normal force of the floor on the crate that helps support the crate. And then finally, a fourth force, that's the frictional force. That's resisting the motion of the crate as it slides across the floor. So those are the four forces. Now, we were told the force F, its magnitude and direction. But we need to calculate the other forces. So let's do that. The weight is easy, because just mass times the acceleration of gravity is 8 kilogram crate times 9.8 meters per second squared. That comes out to be 78.4 newtons. The normal force is a little bit more subtle. So often, crate resting on a floor, for example, the normal force exactly balances the weight. It's equal and opposite to the weight. So it would be 78.4 newtons if this crate was just sitting on the floor. But it's not. It's being pulled. And that pull has a horizontal component that's moving the crate and a vertical component that's helping support the crate. So the normal force doesn't need to be the weight. the normal force is actually less than the weight. Less than the weight by the amount that the force F is helping to support the crate. And that help that's provided by the force F is its vertical component, which is its force times the cosine of 30 degrees. Cosine of 30 degrees will give this the vertical component of F. And so that's something we have to be careful of in this problem. So if you subtract from the weight of 78.4 newtons, this help that's provided by the force F, you get a normal force that's actually 61.1 newtons. So it is indeed less than the weight. Okay, finally we got the frictional force. The frictional force is equal to the coefficient of friction times the normal force. And since we now know the normal force is 61.1 newtons, all we got to do is multiply by the coefficient of friction, 0.12, that's 7.3 newtons. And so that's the sizes and the directions of all the forces that are acting on the crate in that picture. It's a real good summary of what those forces are, how big or small those forces are, and the orientations, the directions of those forces. With that, we can go on and calculate the work that is done by each of those four forces. So let's do that. Okay, so first one, let's calculate the work that's done by that force F that is actually responsible for pulling the crate across the floor. So the work done by the force F is the magnitude of the force times the displacement, delta x, times the cosine of the angle between the force vector, which is 30 degrees above the horizontal, and the displacement, which is in the horizontal. So that's 30 degrees. And so I can just fill in the 20 newtons force, the 1.2 meters displacement, the cosine of 30 degrees. And that comes out to be plus 20.8 joules. Second force, and its work done. Let's take the force of gravity. I'll call that work done WG, the gravity. It's the gravitational force times the displacement times the cosine of the angle between the downward gravitational force and the rightward displacement. And that's 90 degrees. So this is the cosine of 90 degrees. And as you remember, the cosine of 90 degrees, that's 0. And this is an example, we talked about it before, where there is a force, there is a displacement, but the force is perpendicular to displacement, so no work is done. Next force is the normal force, so let's calculate the work done by the normal force. It would be the normal force times the displacement times the cosine of the angle between the normal force and the displacement. But again, the displacement's rightwards, the normal force is upwards, so there's 90 degrees between the direction of the normal force and the direction of the motion, and the cosine of 90 degrees is 0, and so the work done by the normal force is 0. Finally, we got the friction force. The work done by the friction force is the size of the frictional force. It's always the same recipe, always the same formula, just different forces, times the displacement, times the cosine of the angle between the frictional force and the displacement. Well, the displacement is towards the right. The frictional force is towards the left. There's 180 degrees between the frictional force and the displacement. Cosine of 180 degrees is -1. The number comes out to be minus 8.8 joules. And so this is the work done by those four forces that are acting on the crate. So now we can figure out the net work that's done. And the net work that's done is simply the sum of the work that's done by each of the individual forces that were acting. So in our case, it's the force that was applied to the crate, its work done. It's the work done by the gravitational force, although we know that's zero now. The work done by the normal force, and again, we know that's zero now. And the work done by the frictional force, that's non-zero. So we add all these up. Two of them are zero. One of them is positive because that force tends to act in the direction of motion. And for the frictional force, that work done was negative because that acts opposite the direction of motion. And so we've got plus 20.8 joules plus a minus 8.8 joules. This comes out to be plus 12.0 joules. And that's the network that is done. And by the work energy relation, that net work that is done on the crate is the change in kinetic energy. So delta is change, Ke is kinetic energy. And so the change in kinetic energy is also plus 12 joules. The kinetic energy increased by 12 joules. And so this problem was an example of the new concepts of work done by forces and kinetic energy associated with motion. And we were able to calculate using the formula for work done in terms of a force and a displacement. We were able to calculate the work that's done by the force that was applied to the crate, by the gravitational force on the crate, by the normal force on the crate, and by the friction force that was acting on the crate. Once we had those individual works done, we were able to calculate the net work that was done on the crate, the overall, the total, the summed work that was done. And by work energy relation, we now understand that whatever that network that's done is, that changes this kinetic energy, this property of the motion of the object, the crate, the particle, the body. It changes the kinetic energy of that object by that amount, by the amount of work done. So work done sort of is this quantity that we're transferring with the forces to the moving object.